Welcome to the 26th lecture on electronic circuit design. We have been studying class AB push-pull amplifiers in our last few lectures, and we have studied the dual supply and the single power supply based systems, as well as the Darlington pair based amplifier. In this lecture, we will solve an example related to the dual power supply system. So we are given a circuit where VCC is 9 and it's a dual power supply based system, and negative VCC is negative 9. And the amplifier is supposed to drive 50 ohm load, and R1, R2 are 1 kilo ohm. 5 volt RMS is the input applied voltage, AC voltage. Right. So we are supposed to find various quantities. In part A, we will find VB of Q1. So where is Q1? This one, and VB is this. We have to find this voltage VB. We know that since it's a dual power supply based system, the output voltage is 0 volts. The DC output voltage is 0 volt, and it's an NPN transistor where the base voltage is 0.7 volts higher than VB is 0.7 higher than the ground, so it's 0.7 volts. VB of Q2, this VB would be, since it's a PNP transistor, the base should be 0.7 lesser than the voltage of emitter. Voltage of emitter is 0.7 volts, so 0 volts, 0 minus 0.7 is negative 0.7 volts. And the emitter voltage is VE is equal to 0 volts for both transistors because the emitters are common. ICQ is VCC minus VB over R1. We studied that. VCC minus this voltage VB divided by R1 is the ICQ. Since the current mirror, the current computed using this expression, VCC minus VB divided by R1 is the same current that flows through this and this transistor. This transistor in this direction from emitter to collector. So the PNP transistor, the current flows from emitter to collector. So these two currents are the same as this current. VCC minus VB divided by R1. We studied that in theory. So it's a current mirror, and this current is decided by this setup: VCC minus VB divided by R1. So this ICQ comes out to be 8.3 milliamperes, and this is same IC for transistor Q1 as well as for Q2 for both transistors. The next is VCE for Q1. Voltage between collector and emitter. This one, since this is at VCC and it is equal to 9 volts minus 0, so it should be 9 minus 0, 9. And what is VEC for this transistor Q2? We call it VEC instead of VCE because the PNP transistor emitter is at a higher voltage, 0 minus 9, so it's minus 9. So VCE at Q2 is also minus 9, whereas VEC is a positive voltage. Where VCE is a negative voltage for this PNP because this is a PNP transistor. Emitter is at a higher voltage, and this is positive because the NPN transistor, the collector is at a higher voltage compared to the emitter. So the next is to find PL. To find PL, the power dissipated in load. That should be, if you know the voltage drop across this RL, we can use the expression VL squared over RL. So this AC voltage, not DC, because it's a DC 0. DC, it says this is 0 point. So what is the AC VL? Is given to be 5 volts, 5 volt input, 5 volt plus 0.7, 5.7 minus 0.7, again 5. So the max AC voltage that we can have here is 5 volts. So 5 volt RMS. So it is already RMS. So we can directly plug it in the formula VL squared over RL. If it would be peak, we would multiply it by 0.707. So it's RMS, will plug it directly. 5 squared over 50 comes out to be 0.5 watt. And then we come to the part C, where we have to find the Q point for transistor Q1. So it's missing, it's Q1, in fact, Q1. It's a misprint, it's Q1. So we have to find Q point for transistor Q1. For transistor Q1, we have already computed the ICQ in last part, this one, 8.3 milliamperes, and we know it's VCE. VCE of Q1 is 9 volt. We also computed this in the last part A, VCEQ. So we have already computed this Q point, VCEQ1 and ICQ. ICQ is the same because it's the same Q for Q1 and Q2. The same IC for Q1 and Q2. So we have already computed this Q point, and then finally we have to draw it on a scale on this two-dimensional plot where we say we plot VCE on x-axis and IC on y-axis, and this is the point VCEQ, Q point and ICQ. And then we have to find the point IC sat or IC max that we can get through this RL. So what is the max current that we can have through this RL? That is the max voltage that we can have here divided by RL. So the max voltage that we can have here, the AC voltage, we studied that in the theory portion, that is VCC. This is the max AC voltage that we can have here because the swing is like this. The swing is like this. It swings on 0. It swings at 0 volts. It swings at 0 volts and it's like this. So from 0 it goes up to 9 volts VCC or negative 9 volts. This is the max voltage that we can have here at the output without clipping. So 9 volt minus 9 volts. So max voltage is 9. So the maximum voltage is 9 divided by RL is the max current. Right, we have mentioned here 9 divided by 50 ohm. It comes out to be 180 milliamperes. So 180 milliamperes is the maximum current. Then this one. So this is 180 milliampere, quite a large current. It's the max possible current that we can have through this transistor Q1, and this is the actual current that is presently flowing through this. It's 8.3 milliampere. So the transistor is working at a very small current compared to the maximum current that can flow through it. 180 milliampere is the current that can flow through it, but we are working at 8.3 milliampere. Current that is quite smaller than the max possible current. I see saturation current, the maximum current. So that's all for this lecture. In the next lecture, we'll solve a numerical example where we'll discuss the same class AP push-pull amplifier but with the single power supply with VCC, and this negative VCC will be replaced with ground. Right, that's all for this lecture. Thank you.